Good morning. We're at the dawn of a new age in weather prediction. AI-driven weather prediction models offer the possibility for timely, highly accurate, personal forecast. My AI aspiration is the creation of operational, on-demand, data-driven weather prediction systems capable of providing timely, reliable, trustworthy, explainable, and customizable forecast guidance to decision makers. Imagine a future in which skillful, customized forecasts can be delivered to you, tailored to your recreational or business interest. Imagine if short-term predictions of severe thunderstorms and tornadoes were even more accurate and timely than they are today. Imagine better forecasts for extreme temperatures and air quality that help provide public health officials the opportunity to issue timely alerts and advice, reducing health risk associated with heat waves, cold spells, and pollution. Over the last 3 decades, there has been an increase in the number and cost of weather events exceeding $1 billion. These billion-dollar disasters include droughts and fires, flooding and winter storms, hurricanes and severe thunderstorms and tornadoes. Note the growing impact of severe weather and tornadoes, shown in green. While there has been no discernible trend in the number of tornadoes, severe thunderstorms and their associated damages have been on the increase, particularly damage from large hail, as I'm certain insurance companies can attest. The need for timely, accurate forecast for extreme weather events is imperative given the observed and projected increases in frequency and intensity of socially and economically disruptive extreme weather events. Imagine if our country were more resilient to weather disasters because our communities and businesses have the environmental intelligence they need to protect lives and property. For the last 60 years, forecasting has relied on computer-solved physics-based representations of the equations describing the evolution of the atmosphere. These are known as numerical weather prediction models. The process of forecasting natural hazards begins with a routine collection of a broad array of data from satellites, radar, ground and ocean-based sensors, and radiosondes. These data are quality controlled and then assimilated or inserted into these numerical weather prediction models to produce a forecast that is then post-processed and ultimately interpreted by a human forecaster and disseminated to relevant stakeholders. These skillful forecasts are run on high-performance computers for getting the data into the models, running the models, and post-processing the model output to provide actionable information to decision makers. The models are computationally expensive and require about 2.5 hours or so for a global forecast out to about 2 weeks, and this is using hundreds of processors. Enter AI for weather prediction. With the recent emergence of AI weather predictive models, the enterprise of weather prediction is undergoing a transformation unrivaled since the advent of physics-based numerical weather prediction models in the last century. AI will drive our predictive models and allow also the creation of bespoke forecast. So on this image that you see, the model execution shown in the middle will require lower computational expenses. It will run much faster. In fact, it could even run on a laptop, frankly. And then the output can be customized to specific user needs. What we're going to see here is that the cost of these models, again, is much lower to run, and the models are trained on the analyses and observations from the same set of observations that are used to initialize our physics-based models. However, the training is done for these models, and then the models, once they are actually run, can be downscaled to provide output to individuals and businesses for these bespoke forecasts. That 2.5-hour forecast, the time to run the model, I said for this 2-week forecast, 2.5 hours, can be reduced to just about a minute or so on a single GPU. These AI-driven models are fast, as I just mentioned, with execution times anywhere from 1,000 to 10,000 times faster than the conventional physics-based models. The skillfulness and rapid execution time for these models opens the door for more timely forecast with lower computational costs to run, enhanced use of available observations to improve situational awareness, and reduction in forecast uncertainty. And the rapid execution time facilitates generating an ensemble of forecasts capable of more accurately representing the uncertainties in the forecast. However, even with these expected benefits, hurdles in achieving the promise of these models exist. And these hurdles include data limitations, which can hamper the training of machine learning models and reduce the accuracy in some regions, particularly regions where observations are sparse. A lack of trust and understanding of the algorithms that are ultimately developed, as well as concerns about bias, can make forecasters and users hesitant to use these machine learning models, thereby slowing the transition of these models from their development to operations. The training of AI weather prediction models is also computationally expensive, and also the need for greater domain expertise in the model development is certainly required. There are also societal risks as well. The possibility of missing high-impact extreme weather events exist, but mind you, these also exist for physics-based models as well. Also, the post-processing of model output to provide that bespoke forecast that I spoke about before requires knowledge of the forecast consumer, and this certainly raises questions about privacy and security concerns that must be addressed. To achieve this aspiration, we must clear the hurdles and mitigate the societal risk. To do so requires investments in data sharing, infrastructure, compute, human capital, and building trust. Moreover, it requires partnerships across federal, academic, nonprofit, and private sectors. These partnerships require building an open source infrastructure to support community data-driven model development, and the trust is earned through NOAA forecasters evaluating the models in operational environments, including in weather forecast offices and NOAA's model test beds. Models would undergo a spiral development process within which feedback from the NOAA forecasters and test beds is incorporated into model developments and then retested again in operations. AI weather forecasting models will contribute to improving the accuracy and timeliness of weather predictions. The benefits span across various sectors, enhancing public safety, optimizing business operations, and contributing to more effective disaster management and environmental protection. The integration of AI in weather forecasting thus holds the potential to transform how both the public and private sectors respond to and manage weather-related challenges. With AI, weather forecasts can become highly personalized. AI systems can analyze individual user data, such as location and personal preferences, to deliver customized weather information. This could include tailored recommendations for daily activities, travel plans, and outdoor events, enhancing the convenience and relevance of forecast for individuals and businesses alike. Thank you very much for your attention.